Engineering Knowledge Motor, MEO Class 2. This question is: sketch and describe a fuel meter used with high viscosity fuel. Explain how it operates. We all know a fuel meter can also be called as flow meter, which we find between the circulating pump and the supply pump, which always shows a reading which indicates how much fuel has been consumed when the engine runs. Now let's see the flow measurement methods. There are three basic methods of flow measurement. Number one, by measuring the pressure drop across the restriction in a pipe. Number two, by mechanical means. And number three, the recent electromagnetic types. Let's now understand the first method by measuring the pressure drop across a restriction in a pipe, which is either an orifice plate or a venturi pipe. The first method, measuring the pressure drop across a restriction. We have high pressure and low velocity, and after the orifice, that is downstream, we have a low pressure and high velocity. Now, this high pressure and low pressure before and after the orifice can be tapped from here. When we look at this diagram, which is much more simplified, the pressure tapping from the high pressure region and the pressure tapping from the low pressure region is connected to the U-tube manometer, where we have water or mercury or alcohol depending upon the fluid flow. This high pressure acts over the liquid and the low pressure acts over here, and this difference in head, that is difference in pressure, is measured over here. That is, the head of liquid flow is equal to flow velocity. The difference in between the high pressure region and the low pressure region can be measured from the U-tube manometer, and this difference in head, that is head of the liquid, is equal to the flow velocity. So we arrive at a figure where we know the flow velocity. When the velocity of the fluid flow through the orifice is known and the orifice area of cross section is known, it is easy to find out the mass flow rate of the fluid. Let us now calculate the mass flow rate of the fluid. Now we have understood one of the methods by which we can measure the flow of the fluid flowing through a pipeline. Now the second part of the same question asks that: explain the value of the readings and how they are used in calculating the flow value. I assume the same orifice plate being installed in a pipeline, and this is the flow direction. As I said, there is a U-tube manometer connected from the high pressure side and the low pressure side. I assume V1 to be the velocity of the fluid flow before the orifice, and V2 the velocity of fluid after the orifice. In the same manner, pressure P1 is the pressure before the orifice or upstream, and pressure P2 is the pressure after the orifice or on the downstream. Now, as I said earlier, this area upstream is called high pressure and low velocity area. Downstream of the orifice is called low pressure and high velocity area. And We all know from the basics that the mass flow rate in a pipeline is always constant. That is, whatever flows through the upstream of the pipeline per unit time is same as whatever flows on the downstream of the pipeline. And first law of thermodynamics, that is, energy can neither be created nor be destroyed, but it can be transformed from one form to other. With that in mind, the total energy upstream of the orifice is always equal to the total energy downstream of the orifice. That is, the kinetic energy plus potential energy upstream is equal to the kinetic energy and potential energy downstream. Let's now see the calculation. Let's see how the values are useful in calculating the fuel oil flow. As I said, the potential energy and the kinetic energy upstream is equal to the potential energy and kinetic energy downstream. V1 square by 2 is the kinetic energy plus P1 by rho is the potential energy is equal to V2 square by 2 plus P2 by rho. That is the potential energy downstream, and rho is the density of the fluid in kilogram per meter cube. And here you can always substitute the value of the density of the fuel oil used, that is maybe heavy fuel oil, and you can calculate at that temperature. Let's say the fuel oil flowing through the flow meter is 120 degrees Celsius. You can always calculate the density of heavy fuel oil at 120 degrees. And I assume V1 is negligible when compared to V2. The reason, as I said earlier, V1 is the velocity of the fluid upstream or before the orifice, which means it's a low velocity. Since V1 is very, very low, I neglect it. When I rearrange the above equation, I get P1 by rho is equal to V2 square by 2 plus P2 by rho. Again I rearrange, V2 square is equal to 2 by rho into P1 minus P2, where finally I get V2 is the square root of 2 into P1 minus P2 by rho, that is meters per second. And as I said, rho is the density of the fuel oil, and V2 is the velocity of the fluid flowing through the pipeline after the orifice. Since we know the fluid flow velocity V2, we can easily calculate the volume flow rate. Alright, we have derived at a point where we know the fluid flow velocity V2 is the square root of 2 multiplied by P1 minus P2 by rho, meters per second is the unit. Now let us assume A be the cross-section area of the orifice in meter square, V is the volume flow rate at meter cube per second, and M mass flow rate kilogram per second. Since we know that the volume flow rate V is equal to V2 into area of orifice, we substitute that. Let's say the area of orifice is A and V2 multiplied by A, we get the volume flow rate of the fluid. That is, V is equal to, we get a value in meter cube per second is a unit. And we know the density rho is equal to mass by volume. And thus, we know the density of the fuel oil used and the volume flow rate. Substituting this both, we get the mass flow rate of the fluid is equal to density multiplied by the volume flow rate. I substitute the unit for density kilogram per meter cube and for volume flow rate meter cube per second. These both gets cancelled out, and thus I get mass flow rate M is equal to a value, and the unit is kilograms per second. Thus we arrive at a value where we can calculate the amount or the mass of the fluid which has passed through a particular point in a given time. This is how a flow meter works. Let us now have a look at other types of flow meters. This is some mechanical type called as turbine flow meter, where you have turbine rotor blades over here. These are the turbine blades mounted on a rotor, and the rotor is supported here over the bearings. This rotor starts to rotate when the fluid starts to flow. The blade angle and the blade size are designed with specific dimensions to measure the flow accordingly. Here on the rotor there is a magnet, and this magnet, as it rotates, creates a magnetic impulse on this sensor, which then transmits the signal to the transducer. From this transducer we get the mass flow rate of the fuel oil. This type is most commonly not used with high viscosity fuels, but can be used with gas or air or even water. The number of rotation of the magnet, let's say the magnet rotates 100 times, the sensor senses it 100 times, and this is equivalent to say 1 kilogram per second mass flow rate of the fluid. This is how a turbine flow meter works. Let's now discuss about a vane or gear type flow meter. This is a typical vane type flow meter. The fuel oil enters the flow meter in this direction and goes out through this. As it enters, it starts to rotate these vane blades. The vane blades are located here, and there is a smaller gear over here. As the fuel oil goes this way, it rotates the vanes, and this gear engages with this, and this gear starts to rotate. The number of rotation this gear rotates is recorded over here and indicated as the mass flow rate of fuel oil. This type of flow meter is found in most of the ships.